imaginary part of the solution, and theta is going to be the real part of the solution. Because this is a complex valued PDE, we're going to get a complex U, and so we're splitting that into two parts, and then we just have some terms here that'll make it easier to analyze later, like phi is essentially the phase angle here of that imaginary and real part. The rest we'll come back to a little bit later. So how did we approach this from the very start? Because this is a lot. This was confusing to begin with. A really close analogy to this is the heat equation. This is a classic problem, like probably the first thing you start in your PDEs class. Heat equation is like really canon problem. And it looks really similar because we have first partial derivative in time and then second in z. And so that's really similar to what we have going on here, right? And so essentially the heat equation is propagating in time. It is real valued, also non-complex. Propagating in time instead of the PW, which is propagating in z. And so we made this analogy to help derive these Green's functions, which made all this possible later. So I'm going to skip the derivation here, but essentially you do Fourier transform, and then inverse Fourier transform, and then we have this really nice property where the Fourier transform of the convolution of functions is just a product of Fourier transforms. And that gives us a solution right here. And so that is the exact same solution that you could get through your normal PDE analysis in class. That's going to be the exact same thing. But it's really nice and really easy to do numerically, right? Because all we have is a convolution now of your initial condition phi and some Gaussian right there. And so this is really, really nice to start doing in MATLAB and Mathematica, which is what we've done. And this thing right here, so not the initial condition, but G, is what we call the heat kernel. We'll have later a PW kernel. And that is an example of a Green's function for the heat equation. So when we did that inverse Fourier transform to get back, that is the Green's function. So here's our first numerics, right? So heat equation, we all know what's going on. It's just going to decay in time. And we have really, really precise results for that. So 10 to the negative 15th error, numeric error, really, really strong results for, as we'd expect, 1D heat equation, not too complex. So that's a good baseline. Now, our method